So important concepts from the circular motion unit, okay, for the final exam. Okay, very first thing we talked about, there are going to be some questions on the principles of circular motion. Okay, most of those will be multiple choice type questions. All right, things like, which of the following is true for an object undergoing uniform circular motion? Kind of like what you had in your unit exam. A, it's uniformly accelerated motion. B, object traveling at a constant speed, or whatever. Just there'll be some options there. Those would be bad because they would both be true. So I wouldn't have both of those options on there, but just know that stuff like that is going to ask you about the principles of uniform circular motion. So make sure you understand them. Okay, there's a constant force being applied. It's directed towards the center. There's an acceleration towards the center. Okay, all of that kind of stuff are the principles of uniform circular motion. And there's a couple of questions in the multiple choice about that. Okay, then curves. Right, we talked about two kinds, banked and unbanked. It would be important to know how they work. You don't know which one I'm going to ask about, but there's definitely a question about curves in the written response part of your final exam. But there's also a couple of multiple choice questions about curves as well. So if we're talking about an unbanked curve, what keeps me in an unbanked curve, or what acts as a centripetal force? Friction. Okay, so then you set that up as you set up with everything in this unit, centripetal force equals some other force. Okay, remember, centripetal force is always provided by something else. Okay, something else acts as a centripetal force, friction, gravity, whatever it happens to be. Okay, centripetal force is not a force in and of itself. It's a force that other forces can act as. Okay. If we're talking about banked curves, okay, remember we have a special formula for that. The tan of theta equals v squared over r times g. Okay, and that has to do with this whole idea that a banked curve is an inclined plane, okay, where the normal force acts straight out from the plane, and we use its horizontal component to act as a centripetal force. Okay, eliminating the need to rely on friction. If we bank a corner, we don't have to. We'd still do, but we wouldn't have to rely on friction. There would be a speed at which that corner could be negotiated without friction. Fn is not the centripetal force. Fn is the hypotenuse of this triangle because it can only act straight out from the surface, but its horizontal component is the centripetal force, right? That's where we got this formula from, right? Because we said it was opposite over adjacent, okay? The tan of this angle here is opposite divided by adjacent. That's where we got this formula, because it was mv squared over r divided by m times g, right? The opposites divided by the adjacent side, okay? And so that's what gave us this. The mass is canceled, and we were left with that, right? You're not going to have to derive that formula, okay? That formula is already on the formula sheet, but that's how we got it, okay? Mu mg, yeah, because it's friction, right? If it's just mg, that's gravity, right? So it would be mv squared over r equals mu times the normal force, which would be on an unbanked curve, okay, gravity. All right, so there's definitely a problem-solving problem in regards to that. Okay, so we thought that was all of our uniform circular motion stuff. We also talked about, with uniform circular motion, we talked about artificial gravity. That was another example of uniform circular motion, okay? And we said that we had a spinning drum, okay? And a person standing on the inside of that spinning drum wants to go in a straight line, according to Newton's first law, but the inside of the drum prevents that and pushes back towards the center, making them feel like they weigh something, even though they're in a zero gravity environment. This is just using their inertia to push against the surface, which can push back in response and give us that artificial gravity feeling. Okay? Most of our artificial gravity questions ended up looking like this. The centripetal force was provided by the normal force of the cylinder, but we wanted that normal force to feel like gravity. Okay, so that was kind of our artificial gravity stuff. And there could be the odd item, okay, on the final exam about artificial gravity, because again, it's part of uniform circular motion. Okay, then from there we went to non-uniform. Okay, also vertical circular motion. Now, what's the rule for vertical circular motion? Fc equals forces in minus forces out. We dealt with 3 different situations on a vertical circle. We dealt with this situation here, okay, where you're on the top on the inside. In order to do that, you have to be going a minimum speed. Okay, this is the only point on a vertical circle where there is a minimum speed. If I don't go fast enough, I fall. Okay, so in this case here, the force in is gravity. If I'm going just fast enough, the minimum speed, to stay in the circle. If I go faster than the minimum speed, and we talked about this on Friday when we went over your West Ed assignments, okay, if I go faster than the minimum speed, then I push on the track. And what does the track do? Pushes back. And then there's also another force, normal force now, that's acting towards the center. All right? Are there any forces out in this position? No. All right, so in that position there, Fc would equal Fg plus Fn, and there's no forces out. Okay. Other positions we dealt with. Okay, down here, inside on the bottom. What force is that? Gravity. Okay, what force is this? Normal force. Okay, if I'm just sitting at the bottom and not moving, those 2 forces are equal. But you don't really ever do that with vertical circular motion. So as soon as I get moving, Fn will be greater than Fg. And that's why we always feel heaviest at the bottom of a vertical circle, because our inertia wants us to do this, gravity wants us to do this, okay? And the track or the surface or whatever it is has to push really hard on us because we're pushing on it really hard because of those 2 things, okay? So this is where we'd feel the heaviest or the most G forces is here at the bottom, right? So in this situation, we would have Fc equals Fn minus Fg, forces in minus forces out. Okay, the other situation we dealt with was going over the top of the vertical circle. We spent quite a bit of time talking about this one because we watched a bunch of videos on apparent weightlessness. Okay, this is the only situation where, well, actually, you could have a feeling of apparent weightlessness in this situation as well if you were going the minimum speed. Okay, but this is the one where you're essentially always going to feel a little bit lighter than normal. Okay, and you're always going to feel a little bit lighter than normal because normal force is acting out and gravity is acting in. And as soon as you're moving, okay, you've got inertia that wants you to leave the circle. Okay, so you don't push on the top of the circle as hard as you would if you were just sitting on it. Okay, now if I go fast enough, what eventually happens to Fn? Yeah, it becomes 0. Okay, if I go fast enough to actually leave the circle, then Fn becomes 0 and I feel apparently weightless. Everyone all right with that? Okay, so in this situation, Fc equals Fg minus Fn, but like we said, if I go fast enough, Fn will be 0 and I'll be a projectile and I'll feel weightless. Okay, and that's why people on the International Space Station look weightless. They're not actually weightless. They are attracted to the Earth, but because they're always falling, okay, they feel weightless. All right, is that ringing a bell for everybody? Should you expect a vertical circular motion problem-solving problem on the final exam? If you weren't, expect it now, because there is one. Okay. Will there likely be a multiple choice question on that? Yeah, more than likely. Okay, would have something to do with how you would feel probably at some point in a vertical circle, or maybe about minimum speed or something like that. There are 19 multiple choice, and there are 12 written. I don't remember. 80 something. Yeah. Okay. All right. Everybody okay with that one? Yep. As much as I could. It's not perfect. but it's close. Okay, because there's some overlap in dynamics and kinematics, they might seem weighted more. Yeah. Oh, sorry, non-uniform means the speed changes. If the speed changes, that means that the centripetal force changes, the acceleration changes. Everything about this is non-uniform. Yeah. Okay. After vertical circular motion, then we talked about universal gravitation. Okay, that was this one. Fg equals big G times m1 times m2 over r squared. Okay, we spent some time talking about how Newton figured that out, okay, but was never able to make it work until Cavendish came along and did his torsion balance experiment where he was able to determine the value for big G. Okay, once we figured that out, then of course all the physics started to work. We were able to get numbers that made sense and everything was hunky-dory. Okay, on your unit exam, the question about that, in like just that concept, was your net force question about the moon and the earth and the sun. All right, now, do you use that formula in a bunch of other things? Yeah, you use it if you're talking about satellite motion, okay, and things like that. So on a final exam where, you know, I don't want to ask a question on every single concept, this is something that, because it's in another concept, may or may not be tested as a problem on its own. Okay, but because it's part of satellite motion, I can kind of test it in there instead. That doesn't mean, of course, that there wouldn't be a multiple choice question or two about what Newton thought about universal gravitation, especially the part about the force of attraction being, yeah, equal or mutual. Okay, it's a mutual attractive force. Even if this is an apple and the earth, okay, it is a mutual, equally weighted attractive force between the two. All right. Okay, other things that you need to remember about the universal law of gravitation, the relationships within the formula. Okay, if I double the distance between the two objects interacting, what happens to the force? It's a quarter, right? Okay, remember that's inversely exponential. R is squared. Okay, if I double the distance, there's 1/4 the attraction. If I triple the distance, there's 1/9 the attraction between those things. Okay, I increase the mass, I get a linear increase in the force of gravity. All right, then satellite motion. Okay, in all satellite motion, Fc is provided by gravity, right? And not m times g. Okay, so we have mv squared over r equals big G times mass 1 times mass 2 over r squared. There's lots of principles involved with satellite motion. One of the important ones being that there's a mass on both sides of this equation. Because it's on both sides, it'll end up doing what? It'll end up canceling. Which mass is that? The orbiting mass, right? The smaller of the two masses is the one that's going to cancel. So if we're talking about a satellite, okay, orbiting the Earth, it's the satellite's mass that will cancel because all things fall at the same rate, and that's what this force is all about. Okay, so keep that in mind. Okay, that yes, the smaller mass cancels. Okay, and also remember that from time to time we had to do questions where we weren't given V. And we were asked to solve for R, and we ended up having to do the substitution, okay, where we had 2 pi r over t, and we had to plug that in for V. Since V was squared, what did I have to do with this formula? Square it, all right? So I had 4 pi squared times r squared over t squared. And then I just took that, and I put it in for V. Okay, when I did that, what happened to the r's? Yeah, the squared went away, this r went away, and we already know that this m is going to cancel with an m on the other side. Okay, everybody all right with that? Okay, just have to remember how to do that in case the satellite motion problem on the final exam involves that situation. It may or may not, okay? But if it does, it's something you need to know how to do. I was just going to get to that. Okay. So with Kepler, okay, remember we did some problem solving with Kepler's laws. Okay, that was Kepler's law of periods. Okay, as long as two objects orbited the same central body, they had the same Kepler constant. So this formula is true, right? And we said that's fine as long as I have the right information about two objects that happen to be orbiting the same central body. So if it's two planets in the solar system, I can do that because I have always the information for Earth. Okay, if it's a satellite orbiting the Earth, then I probably don't. Right? So we have to make sure that we remember that. This formula is great, provided I have the right situation and the right information. So, okay, that's why we said you can always solve it with this one. Yes, it uses seconds and kilograms and stuff like that, whereas this one can use years and astronomical units. But you have to have just the right information. Any question where you could use this formula, you can do it that way. Yeah, so no, I'm not going to specifically ask a question where I say you have to solve this using Kepler. If you recognize that you could use Kepler and it's shorter and easier, then I'd go for it. But I'm not going to specifically ask a question where you could only use this one, because I can't think of a situation where that would be true. Yeah, okay. So know that that's there, but again, this way we know always works, okay? It's a bit more reliable in that respect, okay? But that doesn't mean that this isn't valid to use. And there could be some multiple choice stuff about Kepler because he was kind of important, okay? Coming up with all of that stuff and orbital mechanics and, the no longer the Earth-centered universe and all that kind of stuff. Okay, and then we talked about gravitational field strength. Okay, so that's little g equals big G times mass 1 over r squared. Okay, remember that formula calculates the acceleration due to gravity at any point. It's different than the force of gravity. Okay, we get this by using the force of gravity. Okay, this force is equal to this force because they're the same force. Everyone okay with that? Right? But all that happens is anything caught in the field experiences the same acceleration due to gravity, which is why the mass cancels off and I'm left with my formula for acceleration due to gravity. Oh. Gravitational acceleration, acceleration due to gravity, or gravitational field strength. Central body, the one generating the field it's caught in. Yeah. Okay. You'll know if you do it wrong, right? Because the answer won't make any sense, right? If you accidentally use the smaller mass here, if you were even given it for any reason, okay, you would get a number that's ridiculously small, okay? Because it would be the acceleration due to gravity due to me, which is nothing. Nothing is accelerating towards me due to gravity, okay? It's just not. You're going to get a number like 10 to the minus 11, okay? It's not going to work. It won't make any sense. If you write that down, it didn't make sense, okay? Don't write it down. Yeah, I would make, if I was going to ask a question about that, I would make sure that the answer was something you could check contextually. Yeah. All right. That's it. That's what's in that unit. That's circular motion. Okay. It was kind of a shorter unit. And it was one that we did pretty well on. Okay. So I would say that, it's probably not one you need to spend as much time on as kinematics and dynamics in terms of if you're planning your studying. Okay. I mean, I still want you to do well on that section, and you did well on that unit exam, but it wasn't that long ago either. Okay. It should be a little fresher in your mind. I don't remember exactly how many of each question there are, but like I say, it's fairly equally weighted. If any unit got shortchanged, it was probably this unit by 2 or 3 marks. Okay, if I was looking at it. All right, questions from you guys? Anything you want me to elaborate on or demonstrate or go over in more detail? Okay, so Kepler had 3 laws that we went over, right? This one was the law of periods. Okay, he also had the law of elliptical orbits. Okay, and he had the law of equal areas, which was the mathematical proof. Okay, so the law of elliptical orbit said that, okay, a planet orbits in an ellipse with the sun at one center. Okay, or sorry, at one focus. Okay, but it never actually looked this way. And then he did the law of equal areas, so sun at the center. Okay, through this elliptical orbit. Okay, every equal time interval swept out equal areas. Okay, of the orbit. All right, when you were further away, you didn't travel through as much of the orbit. Okay, but this area here is equal to this one, where I traveled more along the orbit, but I was closer to the sun, so the areas are always equal. Okay, all right, and that's where we talked about things like why some seasons are shorter than others, some seasons are longer than others, because our winter occurs during the part where we fly through. Okay, which is nice because summer should be longer. It's better, way better, and it's coming soon, very soon. Okay, what else?
We go over a bank curve question.
A bank curve question, okay. Um, Okay, and we're going to assume that this curve is frictionless. All right, so what angle should a 350 meter curve be banked for a safe speed of 20 meters per second? All right, so we're told the speed, 20 meters per second. We're told the radius of the curve, 350 meters, and we're looking for the angle of bank. Okay, so that's going to mean tan of theta equals v squared over r times g. Obviously, we assume that g is 9.81 here, okay, and we're looking for theta. So I'm going to bring tan over to the other side. So theta will be tan to the minus 1 of v squared over rg, tan to the minus 1 of 20 squared divided by 350 times 9.81. How important is it for your calculator to be in degree mode on Monday? Pretty important. Make sure you do that. I'll remind you, because after I clear it, remember it goes back to radians. Okay, so it needs to be banked at 6.6 degrees, which is actually a pretty reasonable bank for numbers I picked out of my head. Okay, what else? Satellite motion we have to substitute. Okay. That's got a little of everything. Like basically every way I could try and screw you up in a satellite motion question, I've put in that one. Okay, so what's the first trick? Altitude. Okay, that means that when I find the radius, I will need to, right, I'll have to subtract the radius of the Earth from that. So that's the first trick. Okay, what's the second trick? Yeah, I gave you this, the time, the period in hours, and it needs to be in seconds. All right, so let's write that down first. Okay, so we're going to have 15 hours times 3,600. Okay, so 54,000 seconds. Okay, FC equals FG, right? mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Don't have V, don't have r. Okay, what do I need to do here? I have to substitute. All right, so I'm going to do this 2 pi r over t thing. I'm going to square all of that, and I'm going to plug it in for V. All right, so I'm going to put mass here first. 2 squared is 4. Pi squared is pi squared. R squared is r squared. Okay, and then I've got t squared underneath. So I basically just put it up against that. That's going to mean that the r on the bottom will cancel. The squared will go away. And now I can manipulate for r. And that's what the question wants me to find. So I'm going to bring t squared over to this side. Okay, so it's gone. The mass of the satellite, which I wasn't given, cancels. So I'm going to get rid of it. Okay, I'm going to bring the 4 pi squared over here by dividing it. Now it's gone. And now I'm going to multiply both sides by r squared. So what's r times r squared? R cubed. All right. Okay, so now I'm solving for r cubed. I just want to solve for r. So that's going to be the cube root of 6.67 times 10 to the minus 11, big G, times the mass of the Earth, 5.98 times 10 to the 24, times the period, 54,000 seconds, squared, okay, divided by 4 pi squared. All right, so okay, now I need to take the cube root of that. Okay, so there's my orbital radius. I'm not done yet. That's how far it is from the center of the Earth. Okay, so I'm going to take that number and I'm going to subtract the radius of the Earth. 6.37 times 10 to the 6. Whoop. All right, so that leaves me with 2.5 times 10 to the 7 meters, right? Okay, so that one would have a little bit of everything in it. Okay, just always be sure you're reading a question carefully. Know what units you're going to need to deal with when you're doing that question, so you get the right units. Because an easy mistake is to plug 15 in, like directly into that formula. Then everything is okay in terms of your work, but you're not going to get the right answer. I did say that, and yes, you will. Well, it would be, like I said, it would be like maybe you'd have to calculate the acceleration to do a dynamics question, like a F equals m times a, right? Something like that. Like nothing with huge overlap. Okay, it's like a car skids to a stop. I give you the information for final, initial, and time. You calculate the acceleration, and then you use that to get the acceleration to do a net force calculation. That would be it. Yeah. Yep. No, if it was possible for a question to be answered both ways, I would have both ways on my key, so you could leave it. Yeah. Okay. Experiences. I don't think I've ever asked you one this way. Okay, so it's a gravitational field strength question, but I disguise it like it's a satellite question to try and throw you. But you're too smart for that. So, okay, it says this satellite experiences an acceleration due to gravity of 1.25 meters per second squared. So here's what we know. G is 1.25 meters per second squared, or newtons per kilogram, whichever way you want to write it. Okay, we know that its orbital distance, okay, that's going to be r, I'm not going to have to add anything, that's center to center, okay, is 6.9 times 10 to the 7 meters. What I'm looking for is the mass of the planet it's orbiting, not Earth. Unless I'm like wildly lucky and it comes out to 5.98 times 10 to the 24, the chances of which are slim to none. If it actually comes out that way, I'm leaving right after that to go buy a lottery ticket. Yeah, don't hold my breath. Okay, so I've got G equals big G times mass of the planet, okay, divided by r squared. So I have r, I'm looking for the mass of the planet, so I'm going to manipulate, it'll be G times r squared over big G, okay, equals m. So that'll be 1.25 times 6.9 times 10 to the 7 squared divided by 6.67 times 10 to the minus 11. Okay, so this planet is heavier than Earth by a lot. Okay, 8.9 times 10 to the 25 kilograms. It doesn't, because exponents are done first, so it would do it first. Okay, done. All right. All right, what else?
Would there be like problem solving questions for artificial gravity?
Mm-hmm. I think that's different than I've worded it before as well. Okay, so in an artificial gravity question, we said that Fc is going to equal the force of gravity. Okay, but in this case, I'm not assuming G is 9.81. In fact, G is what I'm looking for. That'll tell me how much heavier they feel. All right, so we're going to go mv squared over r equals m times G, and we're looking for G this time. What happens to the m's? They cancel. Everybody inside feels the same way, okay, in relation to how they feel on Earth. So I just go v squared over r, and that'll give me the acceleration due to gravity. So 14 squared, whoop, 14, struggle, 14 squared, okay, divided by 200. Oh, they almost feel normal. 0.9, no, sorry, they don't. They feel a 1/10 of normal. Yeah. This is not a very good space station.
Apparently.
Okay. Yeah, this is 1/10 Earth gravity. So lighter than they would on the moon. Okay. Right, you'd go this divided by 9.81, which is what I did in my head and said it's 1/10. Right, because it's going to come out to 0.1. Okay. I probably wouldn't word it that way. I would probably ask what's the acceleration due to gravity, or what would the weight of a this many kilogram person be there, or something like that. Okay, no. A vertical circular motion. Okay. I hope this works out because I just picked these numbers out of my head. Okay. Yep. All right. So here's the situation we're in. We've got a person, okay, who's going over a 200-meter radius hill, okay, at 10 meters per second. Obviously, in that situation, they're going to feel, well, maybe not weightless, but definitely lighter than normal. As soon as you're moving over the top of a vertical circle, you automatically are going to feel lighter than normal. You can't feel heavier than normal in this situation. Okay, you could only feel normal, and that would be if you were just sitting on the top and not moving. Everyone okay with that? Okay, so the situation we have is that we have Fn, probably, okay, and we have Fg. Right, force in, force out. So Fc will equal Fg minus Fn, and I'm looking for their apparent weight. Right, so I'm looking for Fn. So what I would do is add Fn over to this side and then subtract Fc, just so I'm not solving for a negative. All right, so that's going to be m times g minus mv squared over r. So 80 times 9.81 minus 80 times 10 squared divided by 200. I don't think I picked very good numbers, but we'll see. All right, so 80 times 100, sorry, times 9.81 first. Right, minus, I can't believe I just wrote in 80 times 10 squared. Okay, divided by 200. Oh, okay, so that worked out pretty well. So their apparent weight's 744.8, so they feel only slightly lighter than normal, okay, because this isn't very fast compared to the radius of the hill. Okay. And I think actually that's exactly how your unit exam question went. Yeah, okay, I asked you for their apparent weight. Okay, what else, guys? Asking good questions this morning. Minimum speed for a vertical circle? Just the speed you have to take it at? Yeah. Okay, so at what speed can a frictionless 400-meter bank curve, bank curve at 7 degrees? Okay, I have to give you that, I forgot. Okay, so bank curve, so tan of theta equals v squared over r times g. Now we're looking for v. So we multiply both sides by r times g. So tan of theta times rg square rooted will give me v. So the tan of 7 times 400 times 9.81. Let's say that seems kind of big. Yeah. All right, 22 meters per second. I'm picking good numbers today. These are all coming out like they make sense. Yep. Okay, so this would be a Kepler question. As soon as they say the sun, we know we can use Earth. Okay, so we have period of Earth squared over the radius of Earth's orbit cubed equals the period of the asteroid squared over the radius of the asteroid's orbit cubed, and we're looking for the radius of its orbit cubed. So I'm gonna multiply both sides by the radius of Earth's orbit cubed, okay, and divide both sides by the period of Earth's orbit squared, and then multiply radius of the asteroid's orbit cubed over here. So the radius of the asteroid's orbit will be the cube root of 100 squared, period of the asteroid, okay, times 1 cubed divided by 1 squared. Because I'm going to use astronomical units and years. They didn't say what units I had to use, so I use the easiest ones. All right, so all I have to do is take the cube root of 100 squared. So it's 21.5 astronomical units from the sun. No, no, because that factors in a ton of extra stuff and extra geometry. No, we never did one like that, so I wouldn't test you on that. Okay, what else, guys? Well, I wouldn't ask you to find the force of friction, maybe the coefficient.
Or sometimes you give us the force of friction.
I wouldn't give you the force of friction on an unbanked curve. I would give you the coefficient or ask you to find it, one or the other, okay? All right. Okay, so we have an unbanked curve, right? And we're looking for the coefficient of friction, which is kind of a dead giveaway that FC equals the force of friction. Okay, so we have mv squared over r equals mu times the normal force, which on a level surface, which is what an unbanked curve is the force of gravity. Okay, everybody all right with that? Okay, so we're manipulating here to find the coefficient of friction. So when we do that, the masses cancel and G comes over here. Okay, that gets us mu. And then we have 12 squared divided by 9.81 times 125. All right, so the coefficient of friction is 0.12. Yeah, that's pretty slippery. Yeah, that would be a pretty icy, unbanked corner. All right, what else? Okay, anything from dynamics? We didn't get, I think we got pretty well through that though the other day. Okay, boat in a river, yeah. Okay, so this is the first kind of river question where the person is, they're headed straight across. Are they going straight across? No. Okay, they're going to end up downstream. The way you can tell is the question like that will usually ask, how far downstream will they end up? If it asks that, they're not headed into the current. They're not going to end up going straight across if it asks you how far downstream. Otherwise, the answer would be 0. And I wouldn't ask that. Okay, so in a question like this, okay, it would probably be asking for maybe two things. What's the resultant velocity relative to the shore? And how far downstream will they end up? Okay, so if it asks for the velocity relative to the shore, it's asking for this and this, right? Because velocity is a vector quantity, and that's the angle relative to the shore. So, okay, that's just going to be simple geometry here, right? To get V is Pythagorean theorem, right? So we got square root of 4 squared plus 1.2 squared. Whoop. So 4.176 meters per second. And then to find this angle would be the inverse tan of 4 over 1.2. All right, so it'll be 73.3 degrees. Okay, from the shore, all right, because I didn't give you compass directions on that one. So that's the first part. The next part is, how far downstream do they end up? Well, I know the stream is 200 meters wide. Okay, so obviously they're going to end up some distance from straight across down here. All right, so I need to figure this out. I know how fast they're going this way, but if I'm going to find this distance, I need time, just like a projectile motion question. This is a two-dimensional motion question. Okay, I have how fast I'm crossing, and I know I have to go 200 meters at that speed. Can I figure out how long it takes? Okay, so T equals D over V. So 200 over 4 is 50 seconds. All right, so it takes 50 seconds to get across the stream. Now that I know that, D equals V times T. All right, so 50 times 1.2 is what, 60? Yeah, so you're going to wind up 60 meters downstream. You would never use the resultant to get your downstream number. Yeah. If they asked you how far did they travel, then you would actually use that, but I've never asked you to do that. Okay, because how far they travel would actually be the line that goes along here, right? The straight line. Yeah. You could. It should. So yeah, using 200 as this side here, so we'll be looking for, so it'll be inverse, this will be cos, right? So it'll be 200 divided by the cos of 73.3. No, tan, sorry, it'd be tan, yeah. So 200 divided by the tan of 73.3. Yeah. It's just most of the time I don't ask for both. So, yeah. Good. Okay. From dynamics or from, okay. Okay, so law of conservation of energy problem. This ball is rolling down this ramp. It's a really long ramp, I think. Okay, so it's going 60 meters per second when it's 10 meters above the ground, and we're looking for its initial height when initially it was moving at 6 meters per second. All right, so in the absence of friction, okay, this is the law of conservation of energy question where I would have m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. Okay, I didn't give you the mass. Do you need it? No, not in this situation. So we can get rid of the masses and start manipulating for HI. So I'm going to subtract the 1/2 VI and then divide by G. So I'll have this H initial equals 9.81 times 10 plus 1/2 times 60 squared minus 1/2 times 6 squared divided by 9.81. It's going to be very, very high. So yeah, 192 meters. Pretty good size hill. No, because then it's a work energy theorem question. Mm-hmm. Okay, what else, guys? A work energy theorem question? Okay. You ever notice how all my downhill questions angle this way? All my uphill questions go this way? True story. Okay, boring story, but true story. Okay, it's a mess, but it'll work. Okay, so in this question, I have a 20 kilogram box at the bottom of a 40-meter long ramp. Okay, it's going to be pushed up the ramp by 200 newtons worth of force. At the top of the ramp, it's 15 meters higher than it was at the bottom, and it's going at some speed that I'm being asked to calculate. I think this will work. I hope. Okay. So, is work being done here? Yes, because when it gets to the top of the ramp, it's got more energy than it does at the bottom. I'm exerting a force over a distance. I'm doing work. Those are the two ways that I can tell this is a work energy theorem question. Okay, at the top of the ramp, it's going to have more energy, and I'm exerting a force over a distance. So, work equals the change in mechanical energy. Right? We calculate work by multiplying force times distance. Force cos of theta times distance, but I don't need to worry about that. I was told the force in this direction. Okay, that's going to equal the change in mechanical energy. So that will be m times g times h final plus 1/2 mv final squared minus m times g times h initial plus 1/2 mv f squared. Sorry, I told you the mass of the box. Okay, so what am I looking for here? That's supposed to be initial there, not final. I'm looking for VF, so I'm looking for this. All right, so what I want to do then, okay, is move this over here. Okay, because really all this is my initial mechanical. Okay, what I'm doing here is going EF minus EI. So I'm going to move EI over here because the work I do plus the initial energy should equal the final energy. Everyone okay with that logic? All right, so that's my first step then. I'm going to have force times distance plus m times g times h initial plus 1/2 mv initial squared equals m times g times hf plus 1/2 mvf squared. All right, what can I do with this? Not divide it, subtract it. Okay, so bring that over. So force times distance plus mghi plus 1/2 mvi squared minus mghf equals 1/2 mvf squared. Then I divide both sides by 1/2 of m. And square root. Yep, I haven't canceled it yet. All right, so now when I'm going to plug in my numbers, as David just pointed out here, my initial potential energy is 0 because I have no height. It starts at the bottom of the ramp. All right, so what I'm going to end up with here is 200 times, was it 40 meters? Yeah, times 40, okay, plus 1/2 times 20 kilograms times 2, yeah, times 2 squared. Minus 20 times 9.81 times 15 divided by 1/2 times 20. Right, and that should give me my final speed. I hope this works out because I just picked these numbers at random. 200 times, oh, I wrote 400. That's supposed to be just 40. 40 plus 0.5 times 20 times 4 minus 20 times 9.81 times 15, okay, divided by 10. All right, so at the top of the ramp, it's moving at 23 meters per second. Yep. All right, so it ends up looking a lot like a law of conservation of energy question, except EI and EF aren't equal. I just add in whatever extra work is either done or done by the system, in which case it would be subtracted. Right. Like if this was set up differently, it could have also been it's slid down the ramp, and at the bottom of the ramp, it's going slower. right? Because it's lost energy to friction or something like that. Okay, what else? Yes. We're not going to have any like that. Yeah. I'm sure I told you guys that. Okay, what else? Okay, well, you do have the review package. You can have a little more time to look at that. Okay, tomorrow I will take all kinds of questions that you want to ask. Okay, I'll probably come up with a few things here or there just to see what's what. Okay, but for the most part, it's going to be on you guys to ask good questions like you did today, because you kept me occupied almost the entire class, which is awesome. So I'll put that review package up here. It's not that, obviously. That's not the right place. Yep. Okay, there you go, guys.